Hey guys, if you clicked on this video, I'm assuming you're familiar with Snell's law, which tells us about light's trajectory as it passes between two different mediums. Specifically, light will bend to minimize its total travel time. For example, if you wanted to go from point A to point B, but to do so, you'd have to pass between water and air, so swimming and walking, you wouldn't want to spend an equal amount of distance in both of these mediums. In fact, you'd want to minimize the distance that you'd spend in the water, because swimming is way slower than walking. This kind of gives you an intuition why light would want to bend. It might travel a further distance in the air to minimize the swimming time, which looks something like this. Snell's law allows us to find the angle of incidence and the angle of refraction, which is analogous to knowing how light bends. Similarly, given the angles of incidence and refraction, you can have a rough idea of what mediums light may have been passing through. So let's get into setting up our problem. Earlier, I said that we wanted to minimize the total time of light's journey, and this means dividing time into two separate parts: the time you'll spend in the first medium and the time you'll spend in the second medium. So what we're actually minimizing is the sum of these two times. But what is time? Well, if I told you that you were traveling at 5 kilometers an hour for 2 hours, how far would you have traveled in the end? You would say 10 kilometers, right? But what does this tell us? It tells us that velocity times time, velocity is speed and time is time. You might need to go to a more complex video for a true definition of time. But velocity times time is equal to distance, your 10 kilometers. Okay, now what if I want to isolate time now? That would mean dividing both sides by velocity. So you get time is equal to distance divided by velocity. The velocity of light depends on something called the refractive index, which measures how much light bends in a particular medium. And it's found by dividing the speed of light in a vacuum with the speed of light in that particular medium. So we get that the refractive index, we'll say n, is equal to speed of light in a vacuum, c, divided by v, the velocity in that medium. Now we can just isolate v and we'll have an expression for velocity. So v equals c divided by n. And obviously, you'll have two different velocities because you have two different n, or mediums, which each have their own refractive index. Now let's tackle distance. T1, the distance the light travels in the first medium, can be represented as the hypotenuse of a triangle, with x as its horizontal component and y as its vertical component. Using Pythagorean theorem, we can derive an expression for this d1. So you'd have x squared plus y squared equals d1 squared. So d1 is just square root of x squared plus y squared. And that's that. But what about d2? Well, d2 is also the hypotenuse of a triangle. We'll call its vertical component b, but for its horizontal component, we'll have to say that the total horizontal distance traveled by light is equal to L. And that means that the horizontal component of d2 is just L minus x, x being the horizontal component of d1. So now, if we want to isolate d2, we have that d2 squared is equal to, parentheses, L minus x squared plus b squared. Now to isolate d2, we just take the positive square root. So we have d2 is equal to square root of b squared plus and then L minus x squared. So now we have an expression for both of our distances. We also know that the velocity of light in the first medium will be equal to c divided by n1, where n1 is that medium's refractive index, and the velocity of light in the second medium will be c divided by n2, which will also be the refractive index in that medium. Since we now have all the distance and velocities, we can now create expressions for t1 and t2. t1 will be equal to d1 divided by v1, which we know is equal to the square root of x squared plus y squared divided by c divided by n1. For t2, it will be equal to the square root of b squared plus parentheses l minus x squared divided by c divided by n2. And once again, our total time, capital T, is equal to t1 plus t2, which we now know is square root of x squared plus y squared divided by c on n1 plus square root of b squared plus l minus x squared on c divided by n2. So what we're really trying to minimize is this expression. And for calculus students, you know, minimizing means finding the derivative and setting it to 0. By the way, a derivative is just the slope of any given point on that function. So when the derivative is 0, you either have a maximum or a minimum. The function isn't really going anywhere at that particular point. It's common to just set your derivative to 0 and assume that you're talking about a minimum point. This leads us to our first step, differentiating t. To make it a bit easier to see what's going on, let's replace the square roots with powers of a half. So we'll get parentheses x squared plus y squared to the half divided by c on n1 plus parentheses l minus x, well, double parentheses, so parentheses and then parentheses once again, l minus x squared plus b squared to the 1/2 divided by c on n2. So how would I differentiate this? With, well, derivative of t with respect to x. So the first thing to do is our power rule. We have a half as our power. So we'll bring it down as a coefficient. We'll have 1 on 2. And then now we'll be multiplying it by parentheses x squared plus y squared. And then you subtract 1 from your exponent. So we had a half. We subtract 1, which is 2 on 2. So 1 on 2 minus 2 on 2 is minus 1 on 2. So our new exponent will be minus 1 on 2. And of course, we're still dividing that by c on n1. And for our second term, we have a half times, and then parentheses, double parentheses, l minus x squared plus b squared. And now it's also raised to the minus a half. And we're dividing it by c on n2. Okay, we're not quite done yet though, because we're differentiating with respect to x. So now we're using the chain rule, and we've looked at our outer function, but what about our inner function, right? So f of g of x. So now we're gonna look at our x squared. If we were to differentiate just that, we would get 2x. So we're going to multiply this entire thing by 2x. So we have 1/2 times 2x, and then times x squared plus y squared to the minus 1 on 2. All of that divided by c on n1. And for the second expression, we'll get 1 on 2. If we do l minus x squared, if we were to differentiate that, we'd have to do essentially an additional step. So we'd use our power rule, we'd have 1/2 and then times 2 times l minus x. Did our power rule, but we still have a -1 coefficient in front of x. So derivative of minus x is just minus 1. So we'll multiply it by minus 1. And then all of that times our outer function. So we'll go back to l minus x squared plus b squared to the minus 1 on 2. And dividing all of this by c divided by n2. And we can do a bit of simplification, right? On our first term, we have 1/2 times 2x. The 1/2 and 2 cancel, and also this entire portion, our x squared plus y squared raised to the -1/2. A negative coefficient can be brought down to the denominator. A negative exponent, everything that it's exponing exponentiating, we moved to the denominator. So now we get x on, and then I'm going to convert the 1.5 back into square roots. So now in the denominator we have square root of x squared plus y squared. And previously we had divided by c on n1. We can write that out now, flipping the fraction, times n1 on c. So that's what happens when you divide fractions. Flip your second fraction and now it's multiplying it. And let's also cancel the 2's on our second term. A half times 2 cancels. And now we have negative. So instead of doing addition, we'll be subtracting the second fraction. We have -1. So we'll do minus, and then in our numerator we have L minus x. We're going to move this term to the denominator. It has a negative power. And again, I'm going to convert it back to square root. So we have square root of L minus x squared plus b squared. And then instead of being in the denominator, c divided by n1, we're going to actually divide the fractions. So we flip c divided by n1, and now we're multiplying it by our other fraction. So we have times n2 over c. And again, we're setting all of this to being equal to 0. We said that we want to set the derivative to 0 so that we're looking at a minimum point. Okay, so first thing I'm going to do is multiply both sides by c. So 0 times c is still just 0, and it cancels both of the c's. Okay, next I want you to go back to the equations we made at the beginning. And I want you to notice that x divided by x squared plus y squared, which is what we have right here, that was just equal to sine of theta 1, right? If you look at theta 1, it's opposite over hypotenuse. Opposite was x, and hypotenuse was d1, which is just square root of x squared plus y squared. So this can be abbreviated, again, 0 is equal to, now we abbreviate this to sine theta 1. And we already canceled the c's, so we have times n1, refractive index of the first medium, minus, and then let's look at this fraction too. If you look at sine of theta 2, so opposite over hypotenuse, what is the opposite equal to? Well, that was L minus x, and the hypotenuse was the square root of parentheses L minus x squared plus b squared. And that's exactly what we have over here. So that is sine of theta 2. So we have minus sine of theta 2 times n2. Okay, now we can add sine of theta 2 times n2 to both sides. And that will give us sine, well, let's move the n2 also in front of it. So n2 times sine of theta 2 is equal to n1 times sine of theta 1. And that is Snell's law for you.